Hey, what's up? It's Alan. Continuing on with continuity. This section is going to be a little bit different than the ones previous, where it was all limits all the time. We're going to change gears just a touch and talk about this thing called continuity. Why this? Why now? Why not continue with limits and pushing those to new heights? Well, this is necessary in order for us to do that, and limits are also a part of continuity. So they all play within one another in this realm of calculus in this first chapter of calculus, chapter 2. The first blank that we're looking at here is, what do we need in order to discuss this section? Well, we're going to be using that limit concept that we've been talking about and defining in order to explore this new thing called continuity and what it means to be continuous at a specific point. Now, of course, we're going to want to look at the entire function, but it's easy to see graphically, so that's what we're going to start with. Then we'll get to the algebra definition of this thing. What does it mean to be continuous? Well, the easiest way is to explain it by drawing. And if you were to have your pen or pencil and draw the function, whether it be a line, a parabola, cubic, rational, any of those things that we know pass the vertical line test, or just have some relationship. We don't know if it's a function. How can it be continuous if you don't have to lift up your pen or pencil at any point? And if there is a point where you have to do it, then we're going to call that discontinuous, for lack of a better term. It's not continuous at a specific value. Okay, now that's going to be the most important part, because most of these, we are going to put our pen or pen. We don't do dot by dot by dot by dot by dot. We draw smooth, and then if we have to, pick it up and then draw the next part. So where it's discontinuous is going to be very critical for us to figure out where it's not continuous, because everywhere else it pretty much will be. All right, so let's explore this. And of course, let's start by looking at it, getting that visual little bit more comfortableness before we get to the algebra definitions of all these. So as you can see, I've given you 3 different versions of just a line, one that's broken up by what is called a hole. So again, continuous, 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 but then I have to pick up my pen and then continue drawing. So that no good at that value, any value where we have a hole, is discontinuous. Now again, is this a function? Well, yes, not only should you have known that by them telling us f of x, but also it does pass the vertical line test everywhere, even at that discontinuity or jump discontinuity, because yes, it is continuous here, but then I have to begin back over here from left to right, smallest to biggest, which is how we read these things. Even here, still discontinuous at that value a, because although it is a function and only hits one place, I did have to lift up my pen to plot that value and then continue on. These are the things we're looking at. There are, of course, other scenarios that we'll discuss as well, but just wanted to give you an easy synopsis of what it means to be continuous and where it can be discontinuous. So that takes us to our first definition, which you can probably guess what that first blank is. A function f of x is said to be continuous at some point, we're going to call a, if and only if these 3 things happen. Now, of course, what does it mean to be continuous at a point? It's defined at that point, meaning that when we plug in the point in question into our function that was given, then that means we get out some real number. But as you can see why this is in chapter 2, the limit chapter, you can see 2 and 3 require the use of limits. So part 2, first it has to be defined, plug in the value, get a number out, move to step 2. Step 2 says the limit of our function as we approach that value a, it exists. That means from both sides of a, we get the same y value. In words, that it approaches that same y value as we approach from both sides of the x we call a in this case. And then the last step is basically already done for you if you've gone through steps 1 and 2. It literally takes part 1 and part 2 and says that if they are the same value, they're equal, in other words, then it is continuous at that value. So step 3 is literally just a check. If this value, we usually called it L, is equivalent to this value, which again could be some other like M, then if M is equal to L, then it is continuous at that point, because when we directly substituted in that value and got some number out, as we approached from both sides of that value, it also approached some number, and they happen to be the same. Okay, if any of these 3 criteria are not met, then the function is what at that value? Discontinuous. This is the order that you should do them in: 1, 2, and then 3, which stems from 1 and 2, just making sure that they are equivalent. So that's the basis of this whole section. And again, hopefully you see why we have limits in the definition. Therefore, that's why this section is separate but included into the limit chapter, chapter 2. So let's try to streamline this and see if we can't put together some definitions and theorems that we can then utilize throughout whenever we are asked questions that concern limits and or now continuity. Theorem 242 says all polynomial and rational functions are continuous at every single point in their, what do you think? See if you can fill that out before I do. Correct answer was domain. That means wherever it is able to be evaluated, then we should be able to know that it is continuous there. So for polynomials, do we have any issues? What is the domain of a polynomial? Well, that's all real numbers. There are no holes, skips, jumps, or asymptotes. But what about rational, those fractional functions? Are there any issues with those? Yes, of course, rational functions have an issue when the denominator of that function is equal to 0. So again, wherever there is not a domain value, we will have an issue and therefore is not continuous. Everywhere else, all good. And because this is a theorem, it's already been proven, we can simply state that and move on. We know that for a fact. Continue on in your journey or problem. So what other types of functions would we like to try to see where there are, in reality, just the discontinuities? Because everywhere else, it is continuous. So there are basically 4 ways where we can fail to meet that continuity. And so I have them listed here. Let's see if you can fill in any of these blanks. First one should have been pretty obvious. If it's not defined, then no good, because it already fails the very first criteria in order to be continuous. Number 2, a little bit different. It's actually something called a removable discontinuity, which graphically results in a hole. Removable meaning where if we have that issue where our denominator is equal to 0, but we can factor the top and factor the bottom and remove the issue and still be left with a polynomial, well, then it'll look like it's continuous everywhere. But remember, that was not the original function given. We just simplified it. So that is what is called a removable discontinuity, but still a discontinuity. Number 3, a little something called a jump discontinuity. These often happen in what type of functions? That would be piecewise. When we start, say, with a line and then even another line and it jumps like those examples I gave you at the beginning. Last one here, number 4, the function has infinite discontinuities. These are the 4 various ways that we can fail to be continuous and therefore is discontinuous, where it's not defined, a removable discontinuity, a jump, or similar to that, an infinite number of discontinuities. These are the issues that we have. So let's take a look at the next few definitions and try to put this all together in a more formal way. If we have a function that is discontinuous at A, then what happens algebraically? Let's define these. Number 1 here, f has a blank discontinuity at A if f of A does not exist. What do we just call that? Undefined discontinuity. We have to make sure that it's defined first. So if f of a does not exist, then it's undefined. How about part 2? F has a blank discontinuity if the limit of f of x exists. I know this one seems a little counterintuitive because it's saying that the limit actually exists. But if there's a discontinuity, then that means it approached the same number from both sides. But what may have happened? Well, we got a hole there. So that is what is called a removable discontinuity. And I told you when that typically happens is when we have a rational function and we can factor and simplify. Step 3 here. F has a what kind of discontinuity? If the limit from the left and the right both exist, but they are not the same. In other words, we have to jump to get from one side to the other, since they're not the same. And the fourth one, F has infinite discontinuities if from the left we go to positive or negative infinity, or from the right our y values shoot straight up or down. Okay, and again, there are other variations, but just to define those things we just spoke about above, now we have it in a formal setting. And that last one was a nice way to talk about the next definition, because we don't want to look at just both sides all the time. We also need to talk about continuity from one side or the other. Is it continuous just to the left or just to the right? What do you think that means? Well, again, if continuous definition had 3 steps, this would also have to meet those steps, but from one side or the other. So it has to exist, and if it does, the limit from that side has to be the same. Whether it's from the right or the left, that means we will have continuity from the left if it's the negative following it. Remember, that's how we define the left. And of course, if it's positive, then that means the right. Still have to follow those 3 steps of being defined, the limit existing from both sides, and then those 2 things being equivalent to one another, right? We can sum all that up right here for the left and right here for the right. So as we mentioned before, what we're really going to be focusing on is where it's not continuous. We call that discontinuous, because most of these things are going to be continuous over their entire domain. The next theorem here talks about being continuous at L, where that is given by a limit. So our point is L, and we're going to talk about a composite function. So if we were to take this whole thing and say that that is L, we're just looking at f of some number. So if we are to find the limit of f of g of x, remember we said that we could just take and rewrite it as f of that, which would therefore be L, and leave us with. So if we are given that the function f of x is continuous at that value, and we know that the limit of g of x at some a is equal to L, then we know that we can rewrite this limit f of g of x as the function f of the whole limit, which we said was L, so we know that this is a true statement. And of course, there's also other functions that we have discussed in depth. You actually took an entire course on it to try to master it, and those are trigonometric functions. And you can probably guess that sine and cosine are beautiful. They're just like polynomials because they just do this forever in both directions. So how can we generalize this? Because unfortunately, the other 4 trig functions had those vertical asymptotes and either did this or the other ones like this and then that. What do you think? Where did I have to pick my pen or pencil up at? Not a lot of places. So let's talk about the places that I did. Where are those vertical asymptotes? Of course, you can probably guess they're also continuous over their entire domain. So that's pretty much in general. If all else fails and you forget what you're doing as far as continuity goes, you know that if it's going to be continuous, it has to be defined over its domain. That's step 1 of the definition of continuity. So there's one more thing that we're going to discuss, And that is this thing called the intermediate value theorem, or IVT for short. And if you think about the names of a lot of these things, intermediate value. Theorem just means it's been proven, it's something that we can therefore use. But an intermediate value is something that's in between two other values. An in-between or intermediate value. So I put a little synopsis here, and I wanted to let you know that at one point in my life, believe it or not, I was 3 feet tall. And I know you can't see that behind this computer screen, but I'm almost 6 feet tall. So how can I prove to you that I was once 3 feet tall? Well, I can give you, when I was born, I was not 3 feet tall, and my age now, I'm taller than 3 feet. So at some point, whether it was a measured one, or I had a growth spurt at night or one summer, I had to cross through that height of 3 feet. So what we're getting at here on this intermediate value theorem with limits and continuity and all these new calculus terms is the fact that if we are given some closed interval, meaning we are including A and including B, and then we have some other value in between them, we're going to call it C. Well, if we're trying to get some Y value by plugging in that certain C, we're calling that Z. I know a lot of letters here. How can we guarantee that we're going to get that value Z and we can therefore find that unknown constant C? Well, if we plug in A and get out some height, and then we plug in B and get out some other height, if the one that we're trying to find is in between them, what would guarantee that we would go from the lower value to the higher value, or vice versa? How would I get from here to here? What would guarantee me that there is some value in between A and B, whether it's over here, here, here in the middle, or over here closer to B? How would we know that we would be able to get that value we're calling Z? What's the one thing that would have to be true? It would have to be the namesake of this section, continuous. Why would it have to be continuous? Watch what happens if I did this. What if we had a hole there? Well, then no longer are we guaranteed that we'd be able to get that value Z. What if we had a vertical asymptote right there? All those things, the jump discontinuity, any discontinuity is going to be an issue. So that is why it has to be continuous on that closed interval for us to be able to find any in between or intermediate value. Okay, so again, my analogy of my height being 3 feet, you know that I was not born 3 feet, and I grew to be taller than 3 feet. So somewhere along the line, I had to continually grow until I hit that 3 foot mark at one point. So how do we use this more often than just finding some random 3 foot mark or what they're calling Z? Hopefully you guessed what we've been harping on for this entire chapter, the zeros, x-intercepts. Those things are going to be nice for us to be able to find. So if we were to have some graph that we knew was continuous, we could take some of those values, like let's say 1 and 2, and we could plug in 1, get some negative value, plug in 2, get some positive value, and know that since at that point and that point, one of them was negative and one of them was positive, what had to happen? As long as it was continuous, it had to cross our x-axis. Okay, so that's how we'll use this intermediate value theorem more, is to find those zeros, x-intercepts, or roots, we call them, solutions to certain equations. So to give you one last piece of information for this section, 2.48, this theorem that has been proved says, kind of summarizes the whole thing nicely. All the following functions are continuous at every number in their domain. Which one should you put in the first blank? You guessed it, polynomial. And what do we say secondly this works for? Hopefully you said rational functions. Those are two that we've already stated. What are some of the others that we're going to also add on or reiterate? Root or radical functions. This also holds true. Has to be in their domain. Otherwise, it doesn't pass step 1. It's not defined. What else? We said trig form as well as therefore inverse trig form. And lastly, the other two that we've talked often about as well and explored, exponential and logarithmic. That's it for this section. The only thing I want to leave you with one more time is, if you're not sure about continuity and limits, when all else fails, we're going to use direct substitution to find those limits and make sure that we can either find the limit or use that process for the 3 steps that we need to check for continuity. All right, you guys keep working hard. One more section left in this chapter, then we'll pause, review, and make sure that we got this down before we assess. Keep working hard. We'll continue on with continuity and limits in the last section, 2.5.